All right, I want to talk about recursion, tree and graph traversals, depth first search, backtracking, and dynamic programming. Whoops. I know this may seem like a lot, but I'd argue that all of these are pretty much the same thing, and there's very small differences between each of them. And that's sort of why I'm making this video, because I see these topics being taught separately, but really they're about like 95% similar. So let's start with tree and graph traversals, because I've got a good example here. We're going to start with tree first, and then generalize our way to graphs, because a tree is just a restricted form of a graph. Just like how a square is just a rectangle with some constraints, a tree is also just a graph with some constraints. So I have an example of a tree here. This is just a binary tree, meaning that each node has at max 2 children. Binary prefix by means 2. Each node contains 3 attributes that are the actual value. Whoops. The actual value of the node themselves. So like in this case, it's 1. The 1 has a left child of 2 and a right child of 3. Sometimes at the bottom here, the 7 is going to point to none as its left child and 10 as its right child. And all the leaves, 10, 8, 9, and 6, all have both their left and right pointing to none. If you're using Java or pretty much any other language, none is the same as null, but I'm using Python here. If I scroll up a bit, I've coded this out using a class called TreeNode. This class has the 3 attributes that I mentioned before, which are the value of the node and the left and the right pointers, which are initialized to none. In this block of code, I manually set up the actual tree. There are better ways to do this, but I got kind of lazy, so I just hard coded it all out. So root equals 1, and then root.left here equals 2, and then root.right equals 3, root.left.left equals 4, and so on and so forth. But what I mainly want to focus on is this pre-order traversal function. If I do a pre-order traversal of this tree here, which is root and then left and then right, I should get the numbers 1, 2, 4, 7, 10, 5, 8, 9, and then 3, 6. So let's actually run this and see what I get here. So I can just have my terminal open here. I'm just going to run Python and then the name of the file. So 1, 2, 4, 7, 10, 5, 8, 9, 3, 6. All right, that looks good. And I can actually just change this to an in-order traversal too. So if I just take this line and move it down below the recursive statement that goes left first, so that's now left and then root and then right. Save this and run this. And this is the in-order traversal. Lastly, I can actually do the same for post-order. This should be just basic stuff by now, but here's the pre-order, in-order, and post-order traversal of this tree, just so you guys can see it. What does this have to do with anything? Well, with recursion, I pulled up the Wikipedia definition of recursion. It says, in computer science, recursion is a method of solving problems where the solution depends on solution to smaller instances of the same problem. Now, the key idea here is smaller instances of the same problem. In the code for this pre-order traversal, each time I call this pre-order traversal helper function with root.left, which gets initialized to the root, each time at first I'm calling it on the whole entire tree here. Like right here, this is where I actually called the actual function. I'm just calling it on the root. And then each time it gets smaller and smaller. So root.left is now going to be this tree. And then root.right here is going to be this tree, all the way until it gets down to a tree of size 1, which is just the root node. So let me clean this up a bit, and I'll get to the next point, which is going to be depth first search. So I have the Wikipedia definition of depth first search too. It says depth first search is an algorithm for traversing or searching a graph or data structure. The algorithm starts at the root node, which is what we did, and explores as far along as possible along each branch before backtracking. So if we combine the definitions of both of those, for pre-order and in-order traversal, it traverses the tree, it explores as far as possible until you reach the base case along each branch, and it backtracks. And then depth first search traverses the tree, explores along each branch, and also backtracks. Now, these definitions seem like the exact same thing, which is because they basically are the exact same thing. I have this Wikipedia page pulled up, and this is the Wikipedia page for tree traversals. This is a section for depth first search of a binary tree, and it has pre-order, in-order, and post-order here. It also has reverse in-order, which is just instead of left root right, it's right root left. Now, there's one other thing in the definition of a depth first search, and that is it explores as far as possible along each branch before backtracking. So this part before backtracking means it has to hit a place where it knows to go back and search other things. And that place is exactly this base case. That's what the base case is of any recursion, any depth first search. It tells you when to stop looking anymore. So basically, you're going to start at 1 here, right? And then you're going to go to 2, 4, 7, and then you're going to hit none. And then when you hit the none, when root equals none, it's not going to jump into this recursive call anymore. It's just going to jump back out. I could have like a print statement here just to emphasize this further, else print, I don't know, end of recursion, right? This is just a regular base case, right? And all it's telling you is where to stop before you go and search further along. This function explores this entire tree using a depth first search. And in this case, the depth first search, since I put it in the middle, it's an in order. And like I said, if I put it in the beginning again, that's just a regular pre-order. But the main thing here is that a pre-order traversal is a depth first search. And lastly, this idea of backtracking. Where is it? Backtracking, it's a general algorithm for finding all solutions to some computational problems, notably constraint satisfaction problems, that incrementally build candidates to solutions, abandon the candidate as soon as it determines that the candidate cannot possibly be completed to a valid solution. Basically, what this is saying is that it has some constraints. In our case, our constraint was that once a root node equals null, that's when the constraint is held, and that's when it starts to look for other things. It says it incrementally builds candidates. So each time I'm going through 1, 2, then 4, it's incrementally going through one of these candidates. It calls them candidates in this case. It makes more sense in other backtracking problems, but the main point is this: it abandons the candidate once it decides that the candidate cannot be the solution. Once it knows that none cannot be a possible solution here, that's when it abandons it and it goes backwards. So once you hit none all the way down here, which you will get because since this is a pre-order traversal, you're going to go left all the way first. Once it gets to this none, it's going to go back up to 7, and then it's going to go and call the right root.right. And same thing with the 10. When you're at the 10, you'll call root.left, and that'll just be none. And then after you call root.left, it's going to backtrack. That means it's going up a layer in the recursive call stack. So now you're at the point where the 10 is the root, and then it's going to call the next line of code, which is the helper function for root.right. So it's going to call this, then it's going to reach the constraint, and then it's going to go back towards the 10. Now the 10, this function is completely done, right? So then it's going to go back to the 7 again, and then the 7 is going to go up to the 4, and that's how this pre-order traversal is going to work. One last thing I'll say here is that you can actually constrain this problem even further. Let's say I only wanted to explore this part of the tree right here. How I would do that is I would just say something like root.val does not equal 4. Then I would go into this recursive sort of exploration part of my code, because 1 doesn't equal 4, 2, 3, 5, 8, 9, 6, none of those equal 4. So those are all going to go into this block of code. But when the code gets to this 4 right here, it's going to actually jump into the end of recursion statement, and it's not going to explore any of these guys over here. And this isn't very useful for a pre-order traversal, because typically all the pre-order, post-order, and in-order traversals, you want the entire set of nodes in the tree, just rearranging them differently based on which one you're doing. But in general, just for backtracking or exploration problems, you'll see that it's very beneficial to only search for a subset of choices or candidates or different options that you have, and completely ignore everything else. This video is a bit longer than I thought it would be, but in the next video, I'm going to go through this example. It's a problem called House Robber on LeetCode. If you're going through the LeetCode grind, you've probably already done this problem, but I'm going to go through my implementation of it and draw out the recursive tree for it, so you can see how all of these ideas like backtracking and dynamic programming all connect with each other.